Okay,
I guess.
a minute. I guess people are coming in. Okay, well, let's then get started. So welcome back. So we will have the second lecture by Mukund Rangamani on the AdS CFT. Go ahead.
Great, thanks. So yesterday, I started with talking about theories with large number of species, large N theories, and then worked my way towards this decoupling limit in which was discussed by Malasena, and argued that if we look at D3 branes in flat space, then in the particular decoupling limit where I'm sending the string scale to string length to 0, keeping fixed some proper energies, and both down the throat and at infinity, I end up with the near horizon geometry, which is AdS 5 cross S5. And it seems correct to say that the dynamics of the massless sector of open strings on the D3 branes is governed then by the physics of closed strings propagating on AdS 5 cross S5. Okay. So I'll now try to flesh out the correspondence, tell you lots of examples, and then try to set up the dictionary. To facilitate discussion, I decided today to change tactics, and so I decided to write some stuff. So don't get scared that there's a lot of text. I'll walk through this as I go along. I just found that there were too many equations, and my iPad writing is a lot slower than my chalkboard writing. Okay, so let's look at the near horizon limit of the D3 branes. I remind you that the metric of the D3 brane had this function. So the D3 brane sits in 3+1 dimensions. It has a transverse 6 dimensions, and the solution preserves these symmetries. And if I sort of look at the limit I'm taking, alpha prime to 0, keeping this ratio of R over LS fixed, then I take R to 0, I get to keep this factor over the 1. So I drop the 1. That's basically saying that I'm zooming into the near horizon. I get to forget about the asymptotic flat space. And the metric I wrote down yesterday with these harmonic functions h to the 1/4 and so on becomes exactly the metric of AdS 5 cross S5, where I've introduced a length scale, LADS, which basically has information about how many D3 branes were there, what was the string coupling, and what was the string length. So basically, I've just defined LADS to be L string times this dimensionless parameter in terms of G string. Okay. Now, the world volume theory of D3 branes, which I didn't really say much about yesterday, itself is a Yang-Mills theory. It's a Yang-Mills theory with gauge bosons sitting in the adjoint of the gauge group, which I'll take to be SUN. So these are just D3 branes in flat space. We could get other gauge groups if we put orient folds and so on, but I'm not going to do that in the course of this discussion. There are 6 transverse directions to the D3 branes, and the fluctuations of the branes in those transverse direction is also a massless mode. So those are the 6 scalars, xi. We'll think of them as vectors in SO6, or really in the 6th representation of SU4. And then there's a bunch of wild fermions, which also are in the adjoint of SUN. So all the fields are adjoint valued. So everybody here is a matrix. And the Lagrangian is a supersymmetric cousin of QCD. I have normalized the coupling to be 1 over G and Mills squared. There's a standard kinetic term for the gauge bosons, trace at squared. There's a standard kinetic term for these scalars. The scalars carry color charge, so they basically have gauge covariant derivatives, d mu xi. And in addition, there is a interaction term, which is basically xi xj. For those of you who are familiar with the story in n equals 1 supersymmetric theories, the theory can be described as one vector multiplet coupled to 3 chiral multiplets, and there's a superpotential which is epsilon ijk xi xj xk. Okay, where the xi's are now the chiral. So I can say that the superpotential which is epsilon ijk phi I phi j phi k. These are chiral multiples. So this is the theory, and indeed, it's exactly the kind we started with. It's a large N theory, so and has a nice large N limit, and we'll see why we need large N and so on in a second for this theory to make sense. The theory is actually a unique theory in 4 dimensions. It has maximal amount of supersymmetry, and it's actually specified by one complex coupling parameter, which is the complex combination of G Young-Mills squared and the 4-dimensional theta angle. And these map very nicely in string theory to the string coupling and the axion. So the Young-Mills coupling constant maps to the string coupling, and the theta angle of Young-Mills maps to the axion. So the complex axiodilaton, which sits as a complex structure in type 2b, is basically mapped to the complex coupling constant of n equals 4 super Young-Mills. And in addition, we have the length scale. We have the length scale of the AdS space-time, but we also have 2 other length scales in the problem. One, which is a natural length scale seen by strings, the string scale, but another, which is the scale at which quantum gravity effects are important, which is the Planck scale in 10 dimensions. Okay. If I already told you that the AdS scale is determined in terms of the string scale. So this guy I will write as lambda to the 1/4, because I'm going to just define lambda to be G Young-Mills squared n, as I did yesterday when I took the Toff limit. So GSN becomes G Young-Mills squared n, and the string scale in the AdS scale in string units is determined in terms of the coupling lambda. However, there's a relative factor of GS between the Planck scale and the string scale. So if I convert what is the AdS scale in the Planck units, then I find it 4 pi n to the 1/4. And now you see why I need large N. I want my AdS spacetime to be macroscopic in Planck units. If it's not, I'm not really doing anything classical, I'm actually doing quantum gravity. In other words, I can't truncate to tree-level string theory. I'll have to keep string loops and non-perturbative string physics in the game. So I need N very large to ensure that classical strings make sense. A priori, I don't need to take lambda very large. Okay. In fact, the way Toft was thinking about it, Toft was thinking about taking lambda small because he wanted to do perturbation theory at large N. However, if I take lambda small, then the AdS space is of the size of string scale, which means that stringy excitations are just as important in that AdS space as classical gravitational excitations. Okay. In other words, if you look at the spectrum of string theory, we will have to keep not just the low-lying spin 0, spin 1, and spin 2 modes, but also all the higher spin excitations of the rigid trajectory of the string. Now that can be avoided by taking lambda large. Remarkably, the theory doesn't trivialize. what survives are just the classical gravitational effects. So spin 2 and lower survive, while spin 3 and higher get lifted off the spectrum. So what we'll eventually focus on is a limit lambda very large and n very large, which I will call the Toft limit, except that just remember that historically Toft wanted to take lambda small and n very large. So that's the limit, and that's the map between parameters. And what we'll eventually do is work in the limit where we're not even going to study classical string theory, but rather study classical gravity. But for now, let me leave this as the set of statements, and in a couple of minutes, I'll try to sort of simplify this discussion in a slightly more abstract terms for us to have a working definition. But I do want to emphasize that the raison d'etre for AdS CFT is that there is a story that comes from embedding n equals 4 super-Yang-mills directly in 10 dimensions and understanding. And if you really want to understand it, we should understand type 2B strings on AdS 5 cross S5, because that's what's truly dual to n equals 4 super-Yang-mills at arbitrary coupling. But that's not the only example. I picked one because that's nice and nice and symmetric. But over the years, there's a plethora of examples. The ones that I know, obviously, I have filled in this table. So I'll walk you through this. And I've left some gaps in this table. So I'm hoping someone will help me fill this out. So let's start with 4 dimensions. So all examples have gravitational duals of the form an AdS space times some internal space, which I'm calling X. And I'm organizing this discussion by dimension. And I will always use the convention that D refers to the dimension of the field theory. So the AdS space will always be in D+1 dimensions. I've also organized this by the number of supercharges. So I've worked with 8, 16, 8, and 4. Note that I have not listed any non-supersymmetric examples. There are a few, but not all of them are under control. So if someone wants to help me fill out the non-supersymmetric examples, please do so. So the one example we started with is the D3 branes in flat space in 10 dimensions. And that gives us n equals 4 super-Yang-mills dual to AdS 5 cross S5. So that's the example we began with.
Sorry, could I ask a question?
Certainly.
So you filled out this table for some of them, but for some of these entries, is it possible to show that there's other inequivalent to dual pairs?
So you're asking, are there other dual pairs which are not the examples I've listed for the same geometry?
Or maybe I'm wondering, like, are these, like, as anybody showed, like, are these unique? Like, there can't be anything else for, I guess, if you give like certain assumptions about the.
Yeah. So let me say a few words about what I mean by the dual pairs, and then I'll readdress your question. For n equals 4 super-Yang-mills, the theory is unique. So AdS 5 cross S5 is a unique supersymmetric background in type 2B with 32 supercharges, and it's maximally symmetric. It preserves right symmetries of n equals 4 super-Yang-mills. So that part is clear. Let's take your question in the context of n equals 2 theories in 4 dimensions, n equals 2 superconformal theories in 4 dimensions. You can get n equals 2 theories by putting D3 branes not on flat space, but rather take flat space and take the R6 and quotient it by a discrete group, say ZK group. But let's say that ZK only acts on a R4 subspace of R6. This is needed to preserve n equals 2 supersymmetry. In that case, this internal space X, the AdS part doesn't get changed, but the internal space X gets deformed to S5 mod ZK. Okay. Now, the symmetries of this internal space X translates into global symmetries and anomalies, and anomalies of those internal of those global symmetries can be decided from that geometry, as I'll explain in a while. So unless there are multiple theories with the same global symmetries which have different representatives, in which case they really are dual pairs in field theory sense, and therefore they can have the same gravity dual. I don't know of any examples where the theories are not dual in field theory parlance, but happen to be have the same gravitational description. And to make this distinction, it's very important that we actually ask the question in full string theory. Because I could address your question by saying, look, I have a family of superconformal theories in 4 dimensions. They all have AdS 5 duals. Okay, they have some internal space which I'll ignore if I ask certain questions. But consider certain observables, I may completely be able to ignore those internal directions, which is typically how we end up working with AdS CFT. We don't really talk about the internal dimensions unless we're sort of asking some specific questions about these internal dimensions. What that means is that for those class of observables, we have identical answers at leading order in large N from supergravity or string theory. It doesn't mean the theories are identical. It just means that those observables are too restrictive. They can't distinguish theories. Okay, did that address your question a little bit?
It did, thank you.
Yeah. There's another example where you can take a particular Calabi-Yau geometry, the conifold. It's a singular Calabi-Yau in 6 dimensions, and you can put D3 braids on that Calabi-Yau. Locally, the geometries are 6, but instead of the origin, you have a cone, and then this internal space becomes a particular Einstein manifold called T11. Okay, there's an interesting RG flow between R4 mod Z2 and T11 that was discussed a long time ago, and there are various other RG flows that, if I have time, I'll describe for you in this discussion. Rather remarkably, by analyzing the structure of 5-dimensional Einstein manifolds with additional structure, the so-called Sasaki-Einstein manifolds, people came up with an infinite family of 4-dimensional superconformal field theories preserving n equals 1 supersymmetry. So Sasaki-Einstein manifold, I'll give you sort of the sort of hand-waving definition. It's a manifold which is Einstein. It's 5-dimensional. Let's say it's in a 5-dimensional Sasaki-Einstein manifold. It's Einstein with an additional structure, the Sasaki structure, such that if you look at the cone over this geometry, the cone over this geometry is Calabi-Yau. It has a SU3 holonomy. Okay. These geometries are special. They have fibrations, that they have some toric descriptions, and that's how people are able to understand the dual CFTs. They all are given in terms of some quiver conformal field theories. Going 1 dimension lower to three dimensions, the famous example that was also discussed in Maldasena's paper is the world volume theory of M2 branes, which at the time of the AdS CFT correspondence wasn't known explicitly, but now we know that to be a deformation of the ABGM theory, which is described in terms of Chern-Simons matter theories. And that has a dual, which is AdS 4 × S7. This is not a string theory. This is a theory living. This is an M theory compactification because this is coming from M2 branes. Going up is the unique 6-dimensional superconformal fixed point with maximal supersymmetry, the 2,0 superconformal field theory, which lives on the world volume of M5 branes. That is dual to AdS 7 × S4. In both cases, I should note that this comes from n M2 branes and this comes from n M5 branes. There is no obvious coupling parameter in the game in either of these theories. Okay. It's not like n equals for super-Yang Mills. These theories are just prescribed by a discrete parameter n. I believe, and someone can correct me if they know, there should be 1,0 superconformal field theories with holographic duals, probably studied by Wafa and friends in the context of E strings, but I haven't dug through the literature to see what's known about the holographic duals in that case. If so, they're AdS 7 times some other space which is not S4. I have not been able to find satisfactory examples of 5-dimensional superconformal dual pairs. I should say that 5-dimensional superconformal multiplets exist, so by classification. So there ought to be dual pairs. But I did a quick search, and the examples I found all were conjectural or not well studied. So I'll try to fill that table out, or someone can help me fill that piece of the table out. Likewise, in 3 dimensions, I think there should be deformations of the ABGM theory with 8 and 4 superchargers. There's certainly a deformation with 6 superchargers. N=6 theory exists, which is what the ABGM theory is built out of. In fact, the ABGM, the Chern-Simons matter description, is N=6. It's only in some appropriate limit does one get the full 16 superchargers. But again, I wasn't able to fill this out. The other interesting example that's been well studied over the years is the theory with so-called small n 4,4 supersymmetry in 3 dimensions. In 2 dimensions, which comes from the D1, D5 theory. So this is a theory from the near horizon of the bound state of D1 branes and D5 branes in type 2B. And these D1 branes and D5 branes can either be wrapping a 4 torus or a K3 geometry. And in this, the dual geometry is AdS 3 times S3 times either T4 or K3. The relative sizes of T4 and K3 are set by the ratio of the number of D1 and D5 branes. And the AdS scale in this case is given by Q1, Q5, but Q1 is the number of D1 branes and Q5 is the number of D5 branes. So let me just say that here. So this example probably Alex will mention in his lectures next week. There's another interesting theory here, which comes from the intersection of D3 branes, which has similar amount of supersymmetry, but actually a different superconformal algebra. It has slightly larger R symmetry. It's a so-called large 4,4 superconformal theory, a superconformal algebra in 2 dimensions. And this has been conjectured to be dual to string theory on AdS 3 cross S3 cross S3 cross S1. Okay, and there's varying amounts of evidence for this, including a very good match recently of the chiral multiplets, the BPS multiplets in this theory. You can get lower supersymmetry in 2 dimensions by just taking, instead of D1, D5 system in type 2B, but take the D1, D5 system in an orientifold of type 2B with the type 1 theory, and then you can get a similar geometry, but slower supersymmetry because you've taken the orientifold. I believe, and I could be wrong, so someone do correct me, that there isn't a dual with 8,8 supersymmetry in 2 dimensions, which would have 16 supercharges. The one theory that I know is matrix string theory, but matrix string theory describes something else. It doesn't. I don't think it has an AdS dual.
Can I ask a question?
Certainly.
So I was wondering, and I don't know if this is true or not, but is there any organizing principle behind which of these, or how or when you can obtain a holographic dual? Because it seems like there's a lot of disparate pieces, and I'm wondering if there's anything that kind of hints you towards there being, this one should have a holographic dual versus this one shouldn't.
Good. Yeah. So roughly speaking, I'll tell you, I'll give you a better answer in the next page, because I have a set of criteria that we think we want. It's not clear, it's a complete list of criteria.
Okay.
But roughly what we want is large N, so that we have some way to engineer them. And the easiest way to engineer large N theories in string theory is to take large number of branes. You can take a stack of branes, you can take stack of branes which are intersecting, you can do all sorts of things with branes, you can do brain engineering of various kinds of theories. And this laundry list of examples is pretty much obtained by doing those kind of exercises. Okay. Now, what you're really asking is, forget this, how the list was obtained. Let's abstract this away and come up with a criteria which says,
yeah, I'll want to say, okay, now I can say that there should be 35 possible holographic duals, and then I could enumerate those duals.
Good.
Yeah.
So we're just going to do the following. We're going to try to come up with a working definition.
Can I ask a question about the last slide?
Certainly.
You had all the branes of 11D supergravity and type 2b. Why are there no branes from type 2a?
Good. Why are there no branes from type 2a? Well, so I was going to postpone this to the last lecture. All the branes in type 2a, they have non-trivial RG flows. Okay. The D2 brane theory has connections with the M2 brane theory because the D2 brane comes from the M2 brane in 11 dimensions. So there is a conformal fixed point of that theory, which is the M2 brane theory. Okay. Likewise, the D4 brane theory has connections with the M5 brane theory because the D4 brane comes from M5 brane in 11 dimensions. Okay. See, the intrinsic difference is the type 2b theory comes from M theory by a T2 compactification with a T2 shrunk to 0 size. Whereas type 2 comes from M theory by just circle compactification. And strong coupling limits, which are typically interesting, of type 2 necessarily end up in M theory. Okay. So that's a distinction. I'm sure you could engineer various brain models with so in all those cases, maybe the better way to say it is this. When I wrote down the solution for the D3 brane, I only wrote down the metric on the phi form. The dilaton of type 2b was constant in the solution. Okay, that's not true for the other branes, for the type 2 branes, for the type 2a branes. And that dilaton running as a function of the distance from the brane basically means that at different energy scales, you have different descriptions. In some energy scale, you have a description in terms of some supergravity picture. But the true description is either in terms of some free theory or the M theory picture in other energy regimes. So
that sounds somewhat like F theory compactifications.
It's not fully F theory compactification because F theory is really.
I mean the dilaton runs there as well, right?
The dilaton runs there as well, but here it's really a fact that the world volume theories themselves have non-trivial RG flow.
I see. Okay.
That's a theory with 16 supercharges on the D2 brane world volume, which is 2D Yang 2 plus 1D Yang mills. That runs a strong coupling to the ABJM theory. IR fixed point is the ABJM theory. In fact, that's how Seiberg argued for the existence of this ABJM theory, the M2 brane world volume theory, long before AdS CFT or ABJM.
Okay, thank you.
Okay, so let's try to answer the question. What should we look for? What's our sort of organizational principle for holographic theories? Well, basically, we sort of need two things to happen. We need a macroscopic geometry. So we need the AdS scale to be macroscopic in both potentially string and Planck units. So let me start with a string scale. And let's say that I need my field theory to admit something like a planar limit, something like a large N limit. Okay. Now, I'm saying something like a large N limit because if you look through these examples, this column of 4-dimensional field theories, they are all gauge theories. So I can talk about the large N limit the same way I talk about large N limit for Yang mills. This column is also sort of similar, but because it has Chern-Simons theories, so it's fine. This column is less clear because it's not made out of gauge fields at all. The M5 brane doesn't have any, it has two forms, it doesn't have one gauge potentials. Likewise, there seems to be no principle here, because while there are a large number of branes, the world volume theory in 2 dimensions they're not gauge theories. They're just conformal field theories. They're just 2D CFTs. What's common to all of them is that there's some notion of central charge. In 2D, it's really the central charge of the CFT, but there's some notion of central charge, which is large and macroscopic in string units. I won't try to define the central charge unit in some case-by-case basis. So I'm going to take a convenient proxy, which I like, of defining an effective central charge that up to coefficient of proportionality does capture in spirit the number of degrees of freedom. And I'll show you later that the C effective will show up in things like thermal entropy and so on. So it's correct. It's a correct definition up to normalization. What am I going to do? I'm going to take my theory. I'm going to, for now, forget about this internal space. I'm just going to reduce on the internal space by Kaluza-Klein reducing the fields. So I'm going to have a tower of fields in this AdS geometry. When I do the reduction of the parent theory, I will get an effective Newton's constant downstairs in the d+1 dimension, where G Newton in d+1, so 1 over 16 pi G Newton in d+1 is really the volume of X divided by 16 pi, let's say G Newton in 10 dimensions. Okay, so this is my proxy for conveniently normalizing what's happening. If there are dilatons, I have to multiply it by dilatons, but let's say it's just the volume in this case. Simple reduction, direct reduction. Just look at S wave and get this number. But the Newton's constant has dimension of, it has dimension of length to the d-1 in d+1 dimensions. So I'll rescale out the AdS scale to that appropriate power and define a dimensionless central charge to be this ratio. I'm just going to require that this central charge be large. And roughly speaking, this is my notion of classicality, because this is really saying that the AdS scale is large on the effective Planck scale seen by objects in that AdS spacetime. Okay, that's my first criterion. So in this picture, I want to be up here because somewhere down here are quantum strings. And that's my direction of classicality. So if I want to talk about tree-level strings, I should be going up vertically on the C effective direction. But that's not good enough, because you see that will just give me some string theory. I still have to deal with what's happening with those strings. So I'm going to require that in addition, there's an effective coupling parameter, which is, or in the case of superconformal field theories, there's some effective point in moduli space where the stringy nature of the excitations is invisible. In other words, all the stringy excitations are infinitely gapped. Okay, empirically, this is true in all the examples we have. And various people have tried to phrase this as a statement of sparsity of the spectrum. Okay, this is certainly a necessary condition for us to have something like classical gravity. And that I will argue by saying that this lambda, this coupling parameter, which I'm going to parameterize as lambda, I also want to be made large. So stringy effects are dominant on the other side. Okay, I shouldn't say classical string right next to quantum string, but ideally want to sort of suppress stringy effects. By going in that direction. And what I end up with, if I go in this corner, then somewhere up here, way out in the corner of this two-dimensional cartoon parameter space, I have a theory which is basically classical gravity in AdS, coupled to a number of Kaluza-Klein modes coming from this internal space X. And that's the corner we understand very, very, very well. We've started to understand a bit of this corner down here, a bit of this part here for strings on AdS 3 cross S3 cross T4 or K3. And as of a couple of weeks ago, there's a very interesting proposal for understanding the classical string dual of free N-mills. Okay, this has been the holy grail for many years. And there's a very beautiful set of papers by Gabardial and Gopakumar trying to argue for what might be the classical dual for free N-mills. Okay, so that's my working definition. I don't know if that answered your question, Casey, but this certainly are conditions we seem to need. We need some notion of a large central charge. I think we need to sharpen this notion slightly because we also want the OPE coefficients to be suitably down. And I don't know what the correct power, how fast the OPE coefficient will be damped as a function of inverse C effective. And we need a sparse spectrum, and we need some place in the parameter space where stringy effects decouple.
Yeah, this helps as some kind of organizing something that drives you. Yeah, great, thank you.
So there are also various miracles, which is related to the earlier question, which I should point out. These are all miracles that were known to supergravity practitioners over many decades, but they form very useful computational tools in AdS CFT, and they tell you something very interesting about what happens to the theory at large C effective. And this broadly I will classify under the scheme of what's called consistent truncations. And they basically do the following. If I look at type 2b supergravity on AdS 5 cross S5, and if I Kaluza-Klein reduce on S5, I just reduce all my modes, type 2b modes. Supergravity has some gravitons, it has Navier-Stokes 2 forms, it has Ramond forms of varying ranks, and it has axial dilatons. If I reduce them on the S5 by writing them in terms of S5 harmonics of various scalar, vector, tensor harmonics, I get an infinite tower of fields on AdS 5 cross S5 on AdS 5. Okay, we can write down the two derivative action for these fields. It's straightforward. But there are various miracles. A subset of these fields decouples at the quadratic order from other fields. In fact, in other words, there's a subset of fields that don't source another subset of fields, so you can consistently set a large class of fields to 0. The stuff you can set to 0, the remainder basically gets nicely described by 5-dimensional gauge supergravity, a theory which was also constructed a long time ago, and with a gauge group SO6. Okay, this SO6 is basically coming from the isometric group of S5. Even more remarkably, the 5D SO6 gauge supergravity theory admits further truncations. And among the further truncations, there are truncations of the kind which are just Einstein-Maxwell theory, which on Simon's terms, which will be important in a while, or just pure Einstein-Hilbert gravity. And here I mean the following. The truncation to Einstein-Hilbert gravity is such that if you just turn on pure gravitational modes, you will not source any other fields in supergravity. What it means is that you can study solutions of Einstein-Hilbert action and learn lessons that actually are universal to this whole lot of theories. Of course, it doesn't mean that you've solved the problem because you haven't sort of disambiguated the theories, but there's a common subsector of all these theories which is completely described by Einstein-Hilbert action. Okay, so this is another common tactic we use in various computations. We just do these truncations and study truncated set of theories. But again, remember that these truncations can be uplifted into definite examples, and each of the examples comes with its own structure. So,
can I ask a question?
Yeah, sure.
Yeah, just to make sure that I understood the general idea here is that if you make these truncations in both the limits such that you obtain Einstein-Hilbert gravity, then on AdS 5, then that classical theory is dual to a specific sector of each one of those four-dimensional conformal theories.
Correct.
But in general, if you don't take both limits, you take only one or neither of the two, then you should have a like generic complete correspondence between each one of those and the specific string theory.
Correct.
Okay.
Correct. So I'll once I tell you the dictionary between what I'm doing with Einstein-Hilbert gravity and fields and operators, I will tell you what happens, what sector of all those theories truncation to Einstein-Hilbert gravity covers. Okay. Let me give you the answer now, to not keep the suspense. It covers the dynamics of stress tensors of these large C effective theories. Just the stress tensor dynamics, nothing else.
Can I ask a question? You said that the truncation is only consistent at some order in the derivative expansion. Is that right?
No, what I meant is that so the truncations are consistent. When I say so, the couplings between the fields I'm keeping and the fields that I'm ignoring, so the fields I'm keeping source, they couple with the fields that I'm throwing away quadratically. So you know, if let's say a field I'm keeping is metric in 5 dimensions or whatever, it couples to something like through derivative couplings. This is the metric. It couples to something like phi squared.
Right.
Where phi is the field I'm throwing away. It just means that I can throw away phi and not source the metric.
I see.
Yeah, while consistent truncations are very well studied from the point of view of supergravity, I don't know good arguments for why they must exist from field theory. There must be a large enough argument to say that the consistent when consistent truncations are possible. Empirically, we can write down lots of them, and this is how people have been, done various computations over the years. But I've never sort of been able to see a good reverse engineering of that logic to say, okay, the operator dual to this phi must have a certain OPE type coefficient with the stress tensor, so that there's nice decoupling if I look at this large C effective limit. Okay, such statements definitely are true. They should be proven from field theory standpoint.
I see, but they're only approximate in the limit of large C. And then
they're only approximate in the limit of large C.
Good.
Yes.
Good. Great. Thanks.
So that's the expansion. It's not the gradient expansion. There's no derivatives involved.
I see. Just ordinary. I see.
Just
Good. Thank you.
Excuse me, and this result of truncations that are dual to sectors of the field theory, is that true also in other dimensions, or it's a result that we have only for AdS 5?
No, it's true in other dimensions. The truncations to the in both the M theory truncations on AdS 4 cross S7 and S7 cross S4, AdS 7 cross S4 and AdS 4 cross S7, they were known actually before AdS CFT. If I recall my history correct, people proved that the gauge supergravity truncation to AdS 5 cross to SO6 gauge supergravity only post AdS CFT, circa 98 or something like that. The other truncations were known in 80s, as far as I remember. I mean, and I'll just say that many more consistent truncations are known, and to various other subsectors with keeping various, charges, scalar fields, and so on and so forth. Okay, so I won't write an action here because over the time I'll write various actions. But the way I'm going to think about the problem now is I'm going to think about a gravitational theory in AdS which will be given by a d plus one dimensional gravitational action. And I will set the AdS scale to 1 from now onwards. I won't keep track of it. With some matter terms. And depending on what matter you want to study, and what truncations you keep, plus 2 sets of terms, which I will explain in the rest of the lecture. One which has to do with the variational principle, and one which has to do with getting finite observables out of the prescription. Okay. So I'll distinguish what I call the bulk dynamics, which is a d plus one dimensional action, from the boundary terms necessary to make those bulk dynamics consistent, so that there's a good classical phase space, plus counter terms be necessary to make the calculations sensible. Okay, so maybe now is a good time for me to take a pause and check if people have other questions about the general setup. Okay. Just so that we're on the same page, I'm sure many of you have seen this. Let me just quickly go over the geometry of the AdS spacetime. I find it convenient to just think of it as an Einstein manifold with negative cosmological constant. So in this, I actually did put in the AdS scale here. And I'll come back to the picture. We can very conveniently think of this as embedded as a hypersurface, a hyperboloid embedded in d plus 2 dimensions with signature d comma 2. So it's just a fixed locus in this geometry, and this is not just useful for getting metrics. It's actually useful for this embedding space is actually very useful for doing practical computations with conformal multiplets. And given the embedding coordinates, we can just solve for the embedding equation and induce the metric from the flat metric with signature d comma 2 in rd comma 2 to get the global coordinate chart, which I'll parameterize as follows. Okay, I'll use the same coordinates for different charts, but hopefully it should be clear what I mean from context. So the global coordinate chart is basically one where you have rotational symmetry in d minus 1 in d dimensions, and you have a time-like killing field. So this time t is the global time coordinate, and with these coordinates, it's very clear that the geometry is basically topologically a line cross flat space, but it has a boundary. It has an asymptotic boundary, and the asymptotic boundary is time-like because as r goes to infinity, both this term and this term dominate, and the time-like boundary is just a copy of the Einstein static universe, the Lorentzian cylinder r cross st minus 1. So I've drawn the global cylinder here, and time runs up. The radial coordinate r runs in, with r equals infinity being the boundary. If you look at sections of constant t, they're just Euclidean AdS spaces in one lower dimension. They're just negatively curved spaces. There are other coordinates that are useful for calculations, and one which is pretty useful is the Poincare chart, which doesn't cover the global, which is not a global chart, but nevertheless, I'll tell you what it covers. This chart I'll write it in the z coordinates. And this chart covers one Minkowski patch of this Einstein static universe. So it covers basically one conformal section of Minkowski spacetime, and think of wrapping a handkerchief around the cylinder. That's the boundary. That boundary is, in this case, just RD minus 1, 1. In the bulk, it covers one Poincare patch with Poincare horizons, which are ruled by null GD6. So if you cut through the cylinder sort of along a null sheet in the future and past, stuck at this I0 point, then that gives you the domain of the boundary of the Poincare patch. These are the Poincare horizons. And what else do I want to say about this? Yeah, so if you haven't done this exercise, then I do urge you to basically go through figuring out how these coordinates are obtained from the embedding, and also analyzing the geodesic motion to convince yourself that, for example, light rays propagate across the AdS spacetime in finite coordinate time, in finite global coordinate time. And also study the dynamics of, say, a scalar field in AdS, a D+1, and check that a regular solution has quantized energy eigenfrequencies. Okay, so this is an uncompact space, but nevertheless, it's a non-compact space with a growing potential. If you actually try to write down the Schrodinger problem for a Klein-Gordon field here, you'll find that it looks like a harmonic well, and the eigenenergies basically are quantized like a harmonic oscillator with a base 0-point value set by the mass of the field. For practical calculations, at least for rest of today and part of tomorrow, I will work with the Euclidean geometry. And in that case, a Poincare patch is basically a global patch. And I can write it, say this way. Let me just write it as dx squared plus dz squared. I'll reserve lowercase Latin for spatial indices. And the conformal compactification of the Euclidean geometry, the boundary is just a d-sphere. All right, so that's all I want to say about the geometry. So now let's start setting up the basic entries in the dictionary. What do we calculate? Any questions about the geometry? Does someone want me to explain any aspects of this discussion?
Yeah, I have a quick question. You had mentioned that the Euclidean geometry is a global patch. I was hoping you could elaborate a little more on why that is.
Yeah, it's just that the easiest way I can explain this is by thinking about the 2D AdS. Just think of Poincare AdS in the Poincare disk model of hyperbolic space, dx squared plus dz squared plus z squared over z squared. This is the complete disk with the boundary at z equals 0. It covers the entire disk. Okay. The trouble is when you analytically continue x to a time coordinate, it develops causal horizons.
Okay.
So the Poincare coordinates in in pseudo-Riemannian signature, they can analytically continue through to give you the global patch, but there is no such problem in the Euclidean signature.
Okay, thank you.
Yeah.
Question.
Yeah.
In Euclidean AdS, in this metric, this z is equal to 0 is the boundary, right?
Z equals 0 is the boundary, yes.
How we can see from this metric that this is HD, not RD?
Oh, but I said the conformal compactification of it is RD. Here it's a circle. Phi is a circle. I just wrote one dimension, right? So, but it's RD with a point at infinity, because what matters here is the conformal structure, not the local geometry. There was one more question, I thought.
Yeah, I had a question. Is it Poincare patch of AdS or global AdS, which is relevant AdS CFT? Because it seems like you have a boundary R cross SD-1 for global AdS and D-1, 1 for Poincare patch.
Good. Now it depends on where you want to do your field theory. I haven't described other coordinate patches for you. There are other coordinate patches in AdS, which, for example, could have a boundary which is.
I mean, from the near horizon limit of D-brane calculation you did yesterday, you got the Poincare patch, not global.
Indeed. Very good. Okay. Yes. So what I did yesterday, I of course did get the Poincare patch. And if you want to think about conformal field theories in Minkowski spacetime, you would say, let's study the field theory, let's study the geometry in the Poincare patch. However, conformal transformations act more naturally on the instance static universe. So the right arena, I would say, to do, if you're studying conformal field theory and doing radial quantization, is to study them in Lorentz signature on R cross SD-1, because then the conformal compact transformations act nicely. Okay. There's a big difference, however, which is that the time translation generator of global time corresponds to different generator of conformal group than the time translation generator of Poincare time.
Okay.
So this time translation generator corresponds to dilatation generator of the conformal group. This time translation generator corresponds to the usual P0 or zero component of the momentum of the Poincare group. So let me say this. So SOD, 2 is a conformal group, and it's SOD minus 1, 1. The generator of Poincare time translations is the usual time translation generator inside SOD minus 1, 1. What you would usually call Hamiltonian. The generator of translations, time translations here is the dilatation generator, which is sitting inside the SO11 in SOD, 2. So qualitatively different.
Okay. So the CFTs will be related by some kind of transformation?
By a conformal mapping.
Okay.
By a conformal mapping, but which is fine for many observables, as long as you keep track of the fact that CFTs can also have conformal anomalies. So oftentimes when we want to study the most calculations that many people do, we study correlators, for example, in Minkowski space, in which case you might as well study the discussion in Poincare coordinates. Okay, but for some questions, it's nice to study the conformal, the dilatation generator, and then you should just work with the global coordinate chart.
Okay.
But geometrically, the global coordinates cover the entire spacetime, entire Lorentzian spacetime. The Poincare coordinates don't. Okay, so I'm going to elide over the discussion today and do something that which will save me a bit of trouble in setting up the dictionary, which is to work with Euclidean geometry. Okay, I'll pay a price because I'll have to tell you how to convert that calculations to real-time calculations, which will come with boundary conditions on the Poincare horizons. Okay, so we'll go through that step subsequently because I don't want to get tangled with that step a priori in defining observables.
Okay. You might have answered this already, but so the idea is that if you have a superconformal theory on a flat space, on a Minkowski spacetime, then the duality only relates that to the Poincare patch of your AdS spacetime. And if you want a conformal theory which goes to the whole global AdS, then you need to define it on R times S (1).
Correct. Correct. So actually, I let me say something stronger. You can take a field theory and put it on any background you like. Right? You can study a superconformal field theory on whatever background you want to study it on. What was just pointed out, what Anindya just pointed out was that the way I derived the correspondence, I seem to land on my feet in the Poincare patch. Because the D3 branes had non-compact world volume, so I naturally ended up with Minkowski boundary. So there is this, so I'm now going to make one logical leap of saying the correspondence holds with additional prescription of boundary conditions. I can study the field theory on any boundary, provided I find the appropriate bulk geometry. Okay, so here I've given you two boundaries, the Einstein static universe and the Minkowski space. And correspondingly, the two geometries, both are just AdS. No other matter sources turned on. But they talk to different, they describe different parts of that AdS geometry. The global geometry covers the entire space-time. So the field theory lives everywhere. And the Poincare patch covers only part of the geometry. Why is this? So maybe it'll be helpful in light of the questions to say one more thing here. Let's draw a time slice like this. Let's call this t equals 0. When I answered by saying, when I evolve, the time translation generator in global coordinates corresponds to dilatation generator, it means I'm evolving the bulk in time slices that run up vertically on the cylinder. So I slice the cylinder in horizontal segments. That's the global evolution, and that the dual operator in the field theory is the dilatation generator. So it gives me dilatation eigenvalues. When I study the theory in Poincare coordinates, I'm not studying the theory with respect to that time. I'm studying the theory with respect to a different time coordinate. We try to find a different color, which is whose slices are anchored at this I0, and they sort of march up this way. Okay. But this ambiguity is no worse than the usual ambiguity of trying to quantize quantum fields in curved spacetime. Because for every choice of time foliation, which you are allowed, you have a different Hamiltonian. It's just that in this case, the sort of the anchor points on the boundary here, the Poincare coordinate time coordinates sort of end here and here at future Poincare infinity and past Poincare infinity, the I plus and I minus of Minkowski spacetime. The global time, of course, merrily continues. It keeps going because it's just horizontal slicing of the cylinder, and the cylinder is infinitely long. Okay, so but you could pick other slices, okay? So you could pick other slices. So there exists a slice which is a de Sitter slicing of AdS. There exists a slice which is an anti-de Sitter slicing of AdS. You could come up with more exotic slicings. And you could study field theory on all those backgrounds with respect to the appropriate, quantize with respect to the appropriate time coordinate in the bulk. Each would talk to different Hamiltonians in the, from the field theory point of view, because we're asking different questions. This particular connection is pretty straightforward because it's a very simple conformal map from the Poincare patch from Minkowski space to the Einstein static universe.
Does this also mean that if you consider the global patch and the global coordinate chart, and then you study the physics inside the Poincare patch, then that physics must be dual to, in some sense, to both the field theory on Minkowski spacetime and on R times S d minus 1, and the two field theories on those two manifolds must be equal in that sector list?
Well, up to boundary conditions. When you say you study the physics in the Poincare patch, see, let me say something about geodesics. If you look at an observer propagating in AdS, a time-like observer, they will just slosh back and forth. They go through the Poincare patch. They just. So if you're studying something from the global point of view, it enters and exits a Poincare patch. Okay. I mean, of course, there are things you can study which are localized within a single Poincare patch, but if you sort of generically look at the stuff, unless you're the only way to keep within a Poincare patch is to accelerate. But if you sort of ask the question, what's happening, it means that with suitable boundary conditions here and here on the Poincare horizons, you could relate the two things. But they will talk to different. I mean, again, if you take the initial data on this slice and evolve with respect to the Poincare time translation or with respect to the global time translation, you're talking about different pieces of data because one slice just terminates on the Poincare horizon. Good, great. Any other questions, folks? All right. So then let's try to fill out another table, which is the map between the field theory data and the bulk physics. And to make my life simple, I'm going to try to fill out the field theory data in terms of the representations of the conformal group. I could have talked about the representation of the superconformal group, but let's just stick to the conformal group for now. And I'll classify conformal representations using the eigenvalue of the dilatation generator, delta, and spins under the SOD sitting inside SOD commutator. Okay. So I need to say various things. So let's start with scalar fields. And I'm going to sort of go through the generic cases first, and then talk about the exceptional cases, and then talk about some general comments about all of them. So if you have a scalar field of mass m, then if I have a scalar operator, phi, O, this corresponds to a field, let's say of dimension delta. This corresponds to a field of mass m with delta given by d over 2 plus square root d squared over 4 plus m squared. The scalar field, it carries no spin, so representation content under SOD is simple. It carries one quantum number, which is the dilatation quantum number, which is its dimension. So that's a scalar operator. In the bulk, I have a Klein-Gordon field, and the Klein-Gordon field is prescribed by its mass, and the mass is related to the dimension by this famous formula. And note that this mass is bounded from below by the Brighton-Lohner-Friedman bound for the dimension to respect positivity. Okay, I'll come back to an exceptional case in a second. For fermions, spin half particle in the bulk is just a, let's say, Dirac fermion. It has some also described by some mass m. In the boundary, I have a fermionic operator psi delta. Let's use capital psi.
By the way, Mukund, you have about 5 minutes left.
I have about 5 minutes. Thanks, Oliver. This corresponds to Dirac particle of mass m, and the relation between dimension and mass is delta is d over 2 plus m. Okay, let's say plus mod m for definiteness. For spin 1 particles, I can derive a general bound, but let me just focus on gauge fields, which are dual to conserved currents. So let's use AB. So this is a Maxwell field. We can generalize to Proca fields if you like, but I won't do that for now. And dimension of J mu is d minus 1. This is, so here, bulk Maxwell gauge invariance implies boundary current conservation. In fact, the conservation law, d mu J mu equals 0, is simply the radial Gauss law. For spin 2, the boundary energy momentum tensor maps to bulk gravitons, and I'm using uppercase Latin alphabets for bulk indices, and the energy momentum tensor has dimension d. And again, the ADM constraints, I'll explain this tomorrow, they imply energy momentum conservation. Let me talk about a few special cases. And the special cases have to do with what is allowed for unitary conformal representations. A scalar operator is allowed to have a dimension not up to d over 2, but up to d over 2 minus 1. This is the unitarity bound. And so for fields, to get this to saturate this unitarity bound, you have to quantize fields with dimensions in this range differently. They admit alternate boundary conditions to allow, because when m squared is saturates the Brighton-Lohner-Friedman bound, you only get to delta equals d over 2. To go below delta equals d over 2, in this window above the Brighton-Lohner-Friedman bound, you're allowed to impose slightly different boundary conditions than the ones you're allowed to impose above this outside this range. And here, delta is d over 2 minus square root d squared over 4 plus m squared. And the same thing holds for fermionic operators, where the corresponding statement simply says that for mass between 0 and half, we have alternate boundary conditions with delta equals d over 2 minus m. So I'll use the following phrase next time, and then I'll stop. So the standard boundary condition with delta equals d over 2 plus square root d squared over 4 plus m squared, I'll refer to as the Dirichlet boundary condition. And you'll see why. And the alternate boundary condition, I'll call the Neumann boundary condition. And that's the basic entry in the dictionary. It says that for every operator in the conformal field theory, which is completely prescribed by conformal, again, well, representations under the conformal symmetry group SOD, 2, there's a corresponding field in the bulk, and those corresponding fields have quantum numbers which are in one-to-one correspondence with the data of the appropriate operator in the boundary. I will end after saying one sentence. When I say boundary operators, I really mean boundary gauge invariant single trace operators. Okay, for n equals for super-Yang-Mills, these are all single trace operators which are completely gauge invariant. They are not built out of, I'll describe multi-traces and other things separately later. They don't correspond to fields, they correspond to funny boundary conditions. So with that, let me stop and take questions.
Okay. Thank you. Questions?
I have one question. What about at delta equals d over 2? Do you still have two different two different quantizations, or do they in some way overlap with one another?
Okay, so at delta exactly equals at m squared equals minus d squared over 4. You have two degenerate eigenvalues. Both delta plus and delta minus give you the same. Both these signs of delta's equation give you the same solution. Indeed, you have both boundary conditions are allowed. It's a slightly delicate story there because as you'll see when I write down the solutions, there's a solution which is logarithmically different from the other solution. But yes, in that case, both boundary conditions are allowed. I think I'm correct in saying that these are not strict inequalities. They can be saturated.
Thank you.
Other questions?
Another question. Okay, go ahead.
Okay, thanks. I don't know if you explained this yet, but can you maybe re-explain why this operator to field association is the right one for each of the field content of the theory?
No, I haven't explained this. This was my next slide, but or a couple of slides later, but that's for tomorrow. But let me explain it briefly. So the way the story is going to go is as follows. We know from both the area spacetime has the SOD, 2 isometry. So any field propagating on it can be organized in terms of SOD minus d, 2 eReps. The boundary field theory has conformal symmetry, so it has SOD, 2 symmetric global symmetry group. So all its operators can be organized in terms of those SOD, 2 symmetries. Okay. It's just a matter of, as you say, making the identification between the two things. So the way we do the identification is as follows. We try to study the dynamics. We just study the free propagator, free equation for the corresponding field in AdS. So write down the Klein-Gordon equation or the Dirac equation or the Maxwell equation or linearized graviton equation or anybody else. And then you ask the following question. What happens to this field asymptotically as you go to the boundary of AdS? Okay. So all these equations, because they're linear wave equations, the second order ordinary differential, second order partial differential equations. Okay. And I'm only looking at the behavior as I go towards the boundary of AdS. So I just need to know what the scaling solution, what is the solution as I go in the radial direction. So I'll just look at the radial fall-offs. You will find that the fall-offs are dictated by these delta plus and delta minus. That's the first statement. Okay, these deltas are not arbitrary. They come precisely from analyzing fall-off conditions. The second statement is that that's not good enough because I have some field which is satisfying some wave equation. It has some fall-off conditions. So what's the classical phase space which I can use to quantize? So since it's a space with a boundary, I have to give you boundary conditions. Okay. So I can say, I want my fields to have a phase space where the boundary conditions are such that I get a well-defined finite inner product on the classical phase space. So the norm, let's say for Klein-Gordon fields, the Klein-Gordon norm should be positive, should be finite. And like with any other analysis that one has done in, say, flat space or anywhere else, both modes can't be normalizable. In fact, only one of them will be. Which means the other mode needs to be frozen. It needs to be frozen with a boundary condition. Okay. So you freeze one mode and then determine the other mode as a response. But the mode you get to freeze comes with a certain scaling in the radial direction. It has a power law fall off, which I'll argue for you next time from just studying a wave equation. And that fall off is determined by these deltas. So the conjugate power, it should be the power of the corresponding or the source of the operator. So the powers come from delta pluses and minus. These deltas exactly come from those fall offs and freezing and providing boundary conditions.
Okay, I see. Thank you.
Go ahead, Anindya.
Yeah, I have a question. So AdS is not globally hyperbolic, right? So
Yeah.
Is there a subtlety when you time evolve that you need some extra conditions?
Indeed. So indeed, thank you. So what Anindya is pointing out is that I have a space time with a time-like boundary, which means unless I give you boundary conditions for all time, I can't define the initial value problem. The Cauchy problem doesn't make sense. But this is exactly what I want to do if I have a conformal field theory, because if I have a conformal field theory on the boundary, I do want to tell you what its Hamiltonian is for all time, or what sources I'm going to turn on, what I'm going to do to this Hamiltonian for all time. So there's a one-to-one correspondence between the boundary conditions you would prescribe to make the boundary initial value problem of AdS well posed with the statement of what you do to the conformal field theory. So you can think of what's happening with the boundary conditions as a statement of prescribing, telling you what you're doing to conformal operators on the boundary, whether you're turning them on or turning them off at various times. Okay, so indeed, precisely that's where this whole discussion of this table is, because telling you what are the admissible boundary conditions tells you constraints on what the representation content is.
Okay. Thank you.
Any other questions?
Hi, I have a question. So is there a holographic interpretation of gauging the U1 symmetry on the boundary?
Okay. So I do have a special case for you. In D equals 3, the boundary gauge symmetry can, the boundary global symmetry can be gauged. So this is another exception in my list. In fact, it's also true in D equals 2. In fact, in D equals 2, it's the only thing that's allowed. In D equals 3, you're allowed to gauge the boundary current. What does it mean? So let's just ask, what does it mean? If I have a global current which you gauge, it means that you impose the boundary Gauss law. Okay, and just remember, just to be clear for those of you who haven't gotten on the difference, we had a boundary gauge theory to start with, let's say n equals for Yang-Mills of the ABGM theory, that had its own gauge group. We're only talking about gauge singlets for those guys. So that gauge symmetry is not visible. It's never visible in holography. What Jayandi is asking is, if I have a bulk Maxwell theory, then that bulk Maxwell field comes with a gauge invariance. That gauge invariance is not visible in the boundary. What is visible is a boundary component of it, like with any gauge symmetry on a space with boundary. That gauge symmetry becomes a global symmetry. That's the current which is conserved. But you can ask, can I gauge that current? Can I make it dynamical? Can I add a Maxwell term to that boundary theory? And the answer is yes, but only in D equals 3, because you can't, in D equals 3, you can cheat by not really gauging with Maxwell term, but by Chen-Simons term. Okay. The reason you can do it in AdS in D equals 3 or in AdS 4 is because of in the bulk, because of electromagnetic duality. The bulk Maxwell theory has electromagnetic duality. So whatever boundary condition you can put for electric fields, which is the standard Dirichlet boundary condition, by electric magnetic duality you can put for magnetic fields, and that corresponds to gauging symmetry. Okay. In higher dimensions, it fails for reasons that I haven't explained, but it fails for the same reason that you can't impose this alternate boundary condition outside this window. It basically, what would fail is that you would sort of violate the unitarity bounds. You may ask a related question: can I gauge the boundary energy momentum tensor and make the boundary metric dynamical? My answer is no, it cannot be done. It cannot be done without violating unitarity bounds. People have discussed this in the literature, but the clear answer is no.
Any other questions? All right, so if not, thank you, Mukund. And we will reconvene tomorrow. Same schedule. Bye, everyone.